anyway.
Welcome back to Physical Science. Yesterday our video got cut short because of the bell and everybody left. And my computer happened to shut down at that perfect time, so that's pretty cool. So this is the second part of kinetic theory, number 2, notes. Something I want to talk about that we didn't talk about yesterday is kind of under the thermal expansion idea. And we were talking about how things get bigger when they have a higher temperature. Keeping in mind, now temperature is directly related to velocity of the particles. Okay, so for this class, when I say temperature, I want you to think velocity or speed of the particles. There's a little bit more to it than just that. But if I can get you to start thinking that way, then you'll be good. And then heat is different though, because heat then is kind of the summation of all the kinetic energies of all the particles. So if I say you go out in space and I say it's like, 5,000 degrees Celsius, you probably say, no way, it's really cold up there, right? Because you stick your hand out and it freezes, right? Well, that is true.
It's no oxygen can transfer.
But the thing is, the temperature actually is very, very, very high in space. Okay, so remember we talked about temperature being the average kinetic energy per particle. So like if I'm out in space here, I might have one particle flying through at 5,000 degrees Celsius. But if I stick my hand out in space and I get hit by that one particle, is that going to transfer much heat? No. So now down here on Earth, I might be getting hit by 6.02 times 10 to the 23rd pieces at one time on my arm. And so that transfer of all those tiny little kinetic energies then becomes what we call heat. So there can be a big confusion of heat and temperature because of the way that we measure it, the way we talk about it here on Earth. But I want you to know that temperature is the average speed per particle. Heat is all of those energies added up together. Okay, so we talked about thermal expansion. And like what you just saw today, I had, the hole and then the ball, and I heated up the ball with that propane torch, and the ball got bigger, right? It expanded. Because as particles started moving faster and faster and faster, they needed more space, more elbow room, and they expanded. Now, if they would get so fast that the attractive forces and the repulsive forces were kind of evened out, what happens to this solid? It would become a liquid, okay? We'll talk about that a little bit more. But what happened then is I heated this up, and it couldn't fit through the hole anymore because it had expanded. Okay, so we talked about ice being a miracle of life on Earth, or part of it. We talked about how, what is water most dense at? 4 degrees Celsius. You better memorize that. It's most dense at 4 degrees Celsius. That's why we have ice that floats, right? Because if something is less dense, it's going to float in something that's more dense. It's just kind of like the balloon that you get on your birthday that's filled with helium, right? Helium is less dense than air, which is mostly nitrogen and a little bit of oxygen. 80%, 20%. So this helium right here, it takes up the same amount of volume, but it has less mass in it, so it's less dense. Any questions about that? So a balloon floats in air just the same way that ice floats in water. So what is actually making this float is the question. Okay, it's called this. We'll talk about this more in physics, but for this chapter, you still need to know this. There's a force on the ice that is upwards, and that force in this case is called buoyant force, and the word buoyancy, it comes from the same word. Very good. Okay? So buoyant force is something you have to know for this chapter. It's not actually in the notes, so you better write that down. And that's the force that makes something float. So it'll make a less dense object float in a more dense fluid. So liquid is fluid because it flows freely. Air is fluid because it flows freely. Those are both considered to be fluids. Okay, so that's a buoyant force. And then it kind of brings us back into our notes from yesterday. So yesterday we were talking about the kinetic model, and we're talking about gases now. So we talked about solids, liquids, and now gases. And we talked about there's high compressibility in gases. And that's because, like, look at all these, there's, I don't know, 18 dots in here, right? 18 gas particles taking up this amount of space. If this was a solid, it would be 18 particles, but they'd be all like right next to each other. And they'd be locked into a crystalline pattern or a non-crystalline pattern. Difference is a crystalline solid versus an amorphous solid. Remember, that was in the notes before. If we had a liquid, these dots would be spread out on the ground. But notice that, well, if I were to do this perfectly, the solid and the liquid are basically the same density, at least compared to the gas. The gas is way out there. Okay, so I wanted to talk about okay, so this little website here is a good one to look at, because we can see right here that in this first picture that there's a lot of space in the particles, and then the second picture over here, there's less space. And so it's not that hard to compress gas because it's so spaced out the way it is. But I want you to notice here, if you would think of, what are these things here? These are weights, right? There's mass on them. And if you would put a mass on your finger, you would feel a force. Do you agree?
Yes.
So this is forcing down on the plunger, and then that is forcing on the gas particles. Okay, so if you know anything about Newton's third law says that you can't push nothing or you can't force nothing. So if there's a force of a plunger down, the gas particles, all these little pushes here, are going to be equal to this large force that would be the summation of all those forces. That would equal the force of the plunger. Now what do you see here? There's another mass there, right? So that means there's more weight on it, there's more force on the gas. So these particles now are applying more force. Now, did I put any more gas particles in that container? No. So, due to the kinetic theory, why is there more force in this picture 2 than picture 1? Any ideas? I heard some good things out there. The best idea was the pressure part. Okay, so if you think of pressure, pressure is force per area. Okay? So the area then would be like the plunger area, so the area of a circle. And that area didn't change from one picture to the next, did it? No. But if you think of what's happening with these particles here, is they're moving around, right? So if you could hear this particle here hit the side of the container, it'd go like that, you'd hear it, right? And if you heard them all, it'd be like, right? Now, if I hit on my hand, am I forcing on my hand? Yeah, well these particles, when they move and they hit on the wall here, they put a force on the wall. They hit on the wall and they bounce off, just like a bouncing ball would do it, like a super ball. So, what happens when you get, I don't even know what the number is, but 23rd power of 10 particles hitting a wall, then you add up all those little hits into a big force. It's a bunch of small hits. Now, when we compress this down here, what happens is, even if I didn't increase the speed that these particles are going at, there's less distance for it to cover before it hits the wall again. So that means it's going to hit more and more and more times, right? Because there's less distance to cover. So if it's going back and forth in here, the same speed as it's going back and forth in here, you're going to hit more times. Does that make sense?
Yeah.
And if it hits more times, then it's applying more force. Okay. So that's kind of what we wanted to talk about. This is a little example right here of volume and pressure. So you notice here that the temperature is constant. So they're saying that at a constant 300 Kelvin, The pressure here, now to quit moving for some reason, but there you go. You can see the temperature is constant, the pressure increases, and it's just because these particles, even though they're not moving any faster, there's less space for them to cover before they hit again. And that's why the pressure increases, because it's that force is getting faster because it's hitting more often. Okay, any questions about that? Okay, so that's good. That's for those people at home. Gas pressure. Force exerted on a unit of area by gas particles colliding with the surface. Exactly what we talked about. Why does a balloon inflate? Well, when you put more gas particles in there, then they're going to hit more, and so they need more space. That's why a balloon inflates. If you pop a balloon with a pin, you hear the rapid escape of the particles that tears the rubber. Here's your little formula that I just showed you. Pressure is force per area. And Pascal then is the unit, or the SI unit of pressure. So a Pascal is equal to newtons per meter square, which comes, which brings up a joke. Do you want to hear the joke about that? Okay, so that was the joke. No one's laughing. Okay, so 1 Newton. Newton is the label for force. So force is labeled in newtons, and then in the area is a square unit. Meters squared is what we normally use for physics. Okay, so sea level. So if you're on sea level, the atmospheric pressure is 101.3 kilopascals. Okay, so kilopascal is 1,000 pascals, right? So this is 101.3 kilopascals. So that would be, if you're on sea level, the average pressure. Now, if you can see the atmosphere, it actually moves kind of like an ocean waves does. So this is just an average. It would change per day. Okay, atmospheres. The pressure caused by gases is sometimes measured in units called atmospheres. 1 atmosphere would be the pressure like that in San Francisco. 1 atmosphere. Because if you look at this little picture here, if this was you down here, and you're standing, and you had a column that extended all the way up to the top of the atmosphere, and you added all those particles and their weights, okay? So a weight is not a mass, a weight is in newtons. So it took all these little particles, and whatever all those particles weighed, that would put a force on top of your head. And that would be one way to think of how the pressure is applied to you. It's the weight of all the particles above your head. Now the thing is with pressure, since there's so many particles, like remember that green box has 6.02 times 10 to the 23rd particles? There's so many particles, like if this is your hand, right, you have about 15 pounds of pressure per square inch. Like so, 15 pounds on every square inch of your body. So think of all that pressure pushing down. Why can you move your hand up and down then? Well, because the pressure is, think of the particles are hitting you on all sides. So the pressure is pushing up, it's pushing down, it's pushing in between your fingers and your toes and things like that too. Okay? But if you squeeze out that air, then your body would be stuck to the ground. So I don't know if you've seen any of those pressure suits. With that in mind, then, you know, our bodies have come about to live on this environment. So we have this outward pressure that's equal to about 15 pounds per square inch from the inside of our bodies too. So like if we go to space, our blood boils right away because pressure keeps gas inside the blood. And if there's no pressure out in space, then your blood would boil. Okay, so let's see if we can do a problem. Let's change 99,500 pascals to a kilopascal, and then to atmospheres. Okay, so 99,500. Okay, so you guys try this in your book. 99,500 pascals, and we want to get to atmospheres over here. So if you remember how to do this, you know, you're going to show your diagram. Okay, so 1 kilopascal is how many pascals? 1,000, right? Because you memorized that, right? And then we need, so we can see that we cancel out our pascals here. So now we need to have kilopascals on the bottom. Okay, so now we need to look at our relationship from kilopascals, oops, that's a little a, from kilopascals to atmospheres. So that was on the notes. It said 1 kilopascal, or 1 atmosphere is 101.325 kilopascals. Okay, so 101.325 kilopascals equals 1 atmosphere. Okay, so now we can see that we have factored out all the labels. So now we can put it into our calculator. So go ahead and put this into your calculator. You start with this number. What do you do for this piece of it? You divide by 1,000, right? Because it's on the bottom. Then you push equals. And what do you do for this piece of it then? You divide, because the number's on the bottom. So you divide by 101.325, and then you should have your atmospheres. Let's see what you guys get. So if you do that correctly, you come up with an answer of 0.98 atmospheres, and that is the correct answer, 0.98 atmospheres. So you would be up a little bit from sea level. Like here in Bismarck, we're at like 1,650, 1,700 feet above sea level. So on an average day, we would have less than an atmosphere on our body. Any questions on that? Okay, so just kind of some more of the older stuff that we've done with a different conversion factor. Okay, so now we have plasma, which is the highest energy of all. So we have solid is lowest energy, then liquid, then gas, and then plasma. Now keep in mind, when I say lowest energy, I'm talking about temperature, and I'm talking about the same type of substance. Because like you know right here, air, you know that it's gas at room temperature, which is going faster than your desk, which is a solid at room temperature. So when we're talking about this stuff, we're talking about the same substance. Plasma has a tremendous amount of kinetic energy. Like gas, it collides many times a second. The difference is, like if I have gas particles, it's positive and negative atom, hits another positive, negative atom, and bounces off. But plasma is a little different. What happens with plasma is these things hit at such a high energy that when they collide, the positive and negatives kind of loosen up from each other, and then before you know it, you have just a big like sea of negatives and positives random, like kind of all sharing the same space. So that's what plasma is just nuclei and electrons that aren't bound securely to each other. So plasma will be kind of like a sea of this negativity with protons moving around in it. Where gas, the actual atoms stick together with their protons and their electrons, or nucleus and electrons. I say protons, but there's also neutrons in the nucleus. Okay, so where can plasma be found? Surface of the sun or stars, fluorescent lights above our head, exhaust from a rocket, oxyacetylene torch. This probably, that was plasma, that's a propane torch. And halogen lights. Now, if you look at some pictures here, this is all plasma, they say. So what you're seeing in the night skies is stars, which is a plasma form. And then here's a really cool picture too. Lightning is also plasma, such a high energy. So do you have any questions? Okay, so just to kind of make sure you guys are good for the test, I want to sum this stuff up, which again you'll find on your unit organizer. But just so we can talk about what we call the attractive and disruptive forces, and that's just that's kind of these are the forces that are involved when we change from solids to liquids to gases. So, if I have a solid, which force is the strongest here? That'd be the attractive force, right? If I have a liquid, they're both present because it's attractive enough that the pieces stick together as close as they do in a solid, but it's disruptive enough that they can flow freely around each other. If I have a gas, then I'm going to have the disruptive forces, and then a plasma is going to be governed by also the disruptive forces. Okay, now these are also going down in increasing energy. Okay, so increasing energy. And when we talk about this kind of energy, it's kinetic, right? So it's also increasing velocity of the actual particles. So the particles are moving faster and faster and faster as we go down. Kind of like what we said yesterday, we were talking about one atom, a gas atom, and another gas atom. They will collide. Now we said yesterday they don't physically touch, but the word we have to use the word collide because how else can we describe this? And what happens? When these collide, they will bounce off of each other. So that would be, so I'll call this number one, and this is number 2. So they'll bounce off of each other, and they will then do what we call an elastic collision. So there's no loss of kinetic energy when gas particles collide or any particles collide. Now, it doesn't mean that number 1 has the same amount of energy that it did before, but 1 plus 2, as far as energies in this piece, is going to be equal to 1 plus 2 as far as energies in this piece as well. Okay. Any questions? Okay, so hopefully that helps sum things up here a little bit for you and helps you do really well on the test on Thursday.